Okay. So, good evening one more time. For those who came lately, let's start. As I said at 8 o'clock when I joined this meeting, today we'll talk about series of numbers and then power series. I consider that it's good to talk one more time. Actually, it will be a revision. We have the partial exam in 2 weeks, so I think it would be useful to talk more about these topics. So let's start. I shared you my screen. I hope it's visible for everybody. Is it okay?
Yes.
No. So let's start. Okay. So for the moment, let's have a revision on series of numbers. And remember that at this seminar, at the course 2, we learned a lot of convergence tests that help us to study better the convergence of a series. Well, today I will write several series, and for each of them, we'll have to find which convergence test is suitable. Yeah, at the seminar, remember that I wrote you on the blackboard the convergence test, and then we worked. Today, we have the exercises, and for each of them, it's us that we have to guess, yeah, which convergence test is best to use for each situation. So let's do it. The request of the exercise is it's to study the nature of the series. In the series there are, well, I will do in the following way. I will write the series and for it will establish the nature. Okay, so let's take first the series of general term 1 over n times root of order n from n. Then let's see what we can do here. Who can tell me which convergence test it will be suitable? What do you think? Some ideas. Who has an idea? Just try. If it doesn't work, it's okay. Well, do you remember the limit comparison test? So, for instance, for this series, if I take and compare it with the series of general term, and if you remember from the seminar, I said that when I use the limit comparison test, I compare the series with the Riemann series. And at least, can you tell me which Riemann series it will be suitable for this case? What do you think?
1 over n.
Exactly. Good. Who gave me the answer?
Me.
Oh, okay. Good. Yes, you're right. Indeed. What we remark is that 1 over n, I can reduce it. Yeah, I remain with limit. So limit when n goes to infinity from 1 over root of order n from n, And how much is this limit?
1, right? Or
1, isn't it? Because remember, I will write between parentheses limit when n goes to infinity from root of order n from n has the value. How much is this limit?
1 as well.
Yeah, good. So this limit, it's 1, it's between 0 and infinity. We know that in this case, from the limit comparison test, our series, it has the same nature with 1 over n. Yeah, and I write what convergence test I use. It's the limit comparison test. Okay. Next, let's take another series. Today, as I said, we'll talk about series of numbers, power series. We will revise them. Those things are included for the partial exam, so it's a good opportunity to learn and to prepare more for the exam. The next series, it will be the series of general term n over 1 plus 5 power n times n. Okay. Let's see what can be done for this one. Who has an idea? So you see, actually, I repeat, at the seminar, we study the convergence test and we work with it. Now I changed a little. I put the series and we have to guess with which convergence test is suitable. Yeah. At the exam, of course, you will have this kind of exercises. So we have to know well what to do. So, what do you think in this case?
rapport.
Sorry, louder.
Rapport. Criteriul raportului.
Aha. Well. You may try, but it can be something. But let's take, for instance, the general term here. And let's remark something that will help us to finish easily. Here, this term, I see that it's less than n over how much you think? It will be 5 power n times n. Are you agree?
Yeah.
Yeah, but n will go away immediately, and I get 1 over 5 power n. And now, if I will remember from the course and from the seminar too, the series of general term 1 over 5 power n, how it is? Convergent or divergent?
Convergent.
Exactly, is convergent. Why? It's how we called this series. The
series,
louder, please.
the Riemann series.
Well, it's not the Riemann series, it's the geometric series. Yeah, the geometric series. If somebody forgot, let's remember the geometric series. Yeah, it's, as I said, today it's a revision for the partial, so we revise the things we learned. The geometric series, it looks like this. So it will be the series of general term a power n. Yeah, with n from 0. Well, what do we know about this series? Is convergent if and only if. What happens? Who can tell us? A, it's where, in which interval?
1
Minus
infinity.
1.
It's
Minus 1, 1.
exactly. Good. Who said?
Me.
Good, Maria. Yeah, very well. When you talk, that's why I ask you, because I have only my OneNote board in front of my eyes. I can't see the screen where your names they are. So yeah, I want to know with who I'm talking. Good. So remember about what happens with the geometric series. It's convergent. So of course, first of all, it's the series of general term a power n, and remember that is convergent if and only if a is in -1, 1. Good. So now I will come back here. I have for my series that the general term is less or equal than 1 over 5 power n, but the series of general term 1 over 5 power n is convergent. So what will follow immediately and why? What will happen with our series?
No. It's gonna converge.
Exactly, it's convergent. Yeah. Do you remember which convergence test we use here?
Direct comparison test.
Exactly, the comparison test. Okay, comparison test. Good. So the series is convergent. All right, the next one. But by the way, questions till now? Anytime you have a question, it's okay. You can interrupt me. I don't mind and ask. All right. So questions till now? Okay. Let's go further. Exercise C. I will take another series, for instance, the series of general term n plus the logarithm of n over n squared plus 1. Okay, let's see what we can do for this series. Who has an idea? Well, yeah. Yeah, please.
We can compare it with
Yeah.
qn over n squared plus 1, since logarithm of n is more than n.
I think here it's not necessary to compare it with 1 over n squared plus 1. I think that's what you said, isn't it? If you look, actually, it's okay if I will compare it just with 1 over n.
Yeah, that makes sense. As well.
Yeah. Yeah, you may finish your sentence.
Yeah, because we were going to go back anyway. Like, I was gonna say that you you compare to n over n squared plus 1, and then you compare back function with 1 over n, since they both have the same like power order.
Exactly. That's the idea. Yeah. So what I have here is I have the same power. To be more clear how much it would be this limit, maybe someone, well, the value of the limit is 1, but to be more clear for everybody that this limit is 1, what can I do? I can take n squared as the common factor, so we force it, and immediately I will get n squared from the numerator. We get n squared, it will be times 1 plus, it will remain only the logarithm of n over n, and at the denominator we get n squared times 1 plus 1 over n squared. Right, n squared goes away, and now I get how much limit when n goes to infinity from 1 plus the logarithm of n over n, everything over 1 plus 1 over n squared. Okay, but 1 over n squared, everybody knows that's 0. How much it is the logarithm of n over n?
0.
Exactly, because I remember you from high school, the logarithm is slower, yeah, goes slower than the polynomial functions to infinity. So yeah, logarithm of n over n is 0. Well, the all limit will have the value 1, and I finished. But now, because the value of that ratio is in 0 plus infinity, one more time, I will apply the limit comparison test, and the series from my exercise, it seems that it has the same nature with 1 over n, which I suppose that everybody knows that's how, convergent or divergent. One over n is the harmonic series, so it's
Divergent.
yeah, divergent. Good. Okay, let's continue. And just a second. Okay, let's continue with something else. Exercise D. Okay, let's take in this case, for instance, the series of general term 1 minus cosinus of pi over n. Okay, let's see what can we do here. What ideas do you have? Who can help me? Well, in this situation, to be easier to study the convergence of my series, let's remember the following trigonometric formula. 1 minus cosinus of, well, actually it is of 2x over 2. So here it's 2x. Yeah. That's sinus squared of x. I have this formula from high school. Yeah, do you know it?
Yes.
Just a second, because I'm not sure that. Okay, I'm curious. I want to see if the recording is okay. For you, it is visible that the application is recording our meeting.
Yeah.
It's okay, yeah?
Yeah.
Because I need to record this meeting, it's important. First of all, because not all students join this meeting, and if someone wants to know what we discussed, it has the possibility to see the recording. But of course, I don't advise you to just to follow the recording. It's better to attend these meetings because it's something else. At these meetings we discuss. If you have questions, you may ask. So it's more useful to attend the meetings. Okay, so I have this equalities, this trigonometric equality. Now, by using this, actually I get the fact that the general term of the series, it will be 2 times sinus squared of, it will be how much? Pi over 2n. Yeah, because what happened? In my case, I regard pi over n as 2x. So obviously, the argument of sinus, it will be pi over n over 2. Yeah. So I got the fact that the series, it's actually 2 times the series of general term sinus squared of pi over 2n. Okay. Good. Let's see what we can do here. What ideas do we have? It's easy. Just concentrate a little. We can use one of the convergence tests we already discussed today. So what can I do now for sinus squared of pi over 2n? What to use?
I think you can compare it to pi squared over 2n squared.
Exactly. Or I can say with 1 over n squared directly, because pi, it's a constant.
Yeah.
And a constant, I said that at seminars several times, a constant doesn't change the nature of a series. Yeah, but it's okay what you said. Good. So I will use actually the limit comparison test one more time. And let's take and compare it. So I want to compare the series from our exercise with 1 over n squared. Okay, but to be able to compute this one, I will put here pi squared, and also here it's 2n. Yeah, I wrote by mistake at the denominator to pi. It's 2n. Okay, pi squared, and also it's missing someone. Who? The b. I think you can guess what I will do. I will use the remarkable limit sinus of x over x. So it's missing someone here. How much?
2 squared.
No, it's 4. Yeah.
Yeah, 4.
All right. I don't want to change anything, so I will quickly multiply by the reverse, pi over 4 over pi squared. Okay. That's actually pi squared over 4 times limit when n goes to infinity from sinus squared of pi over 2n over pi squared over 4n squared. But by using the remarkable limit, and I will write it over here for those who, I don't know, maybe someone who forgot it, but I doubt that. Anyway, remember that this limit is 1, so the whole limit becomes pi squared over 4, which is a value lying in the interval 0 plus infinity, which means that our series, it will have the same nature with the Riemann series of general term 1 over n squared. So the series, how it will be? Convergent or divergent? What do you remember? Is it convergent or divergent?
Convergent.
Convergent. Thank you. Okay, so it's convergent. One more time, I used the limit comparison test. All right, the next one. Let's take, for instance, the series of general term n factorial times 6 power n, everything over n power n plus 3. Okay, let's see for this series, what can we do here?
We can use the ratio test.
Good. We can use, yeah, we can use the ratio test. Good. Let's do it. So if I denote by an the general term of the series, then by using the ratio test, I take limit when n goes to infinity from an plus 1 over an. I will perform the computations, of course. That will be limit when n goes to infinity. And now let's replace an plus 1. That's n plus 1 factorial times 6 power n plus 1. Everything over n plus 1 times, it will be n plus 4 times the reverse of an, which is n power n plus 3, everything over n factorial times 6 power n. Okay, now let's make all the simplifications. So we get what we get here. I will simplify by 6 power n. Just a second. So 6 power n. It remains only 6. N factorial also, it will be reduced. We remain with n plus 1. So till now, I get 6 times n plus 1 times n power n plus 3, n plus 3, everything over n plus 1 power n plus 4. Okay, if you look, there is one more term that works to simplify it, to reduce it. So in the end, we get 6 times n over n plus 1. Okay, I will write it n plus n power n plus 3, everything over n plus 1 power n plus 3. Just a second, I want to see something. Okay, sorry, I wanted to check if there are students who ask us to join the meeting. Okay, let's come back. Now, what I will get here, it will be 6, the constant, goes in front. So we get 6 times limit when n goes to infinity from n over n plus 3. Sorry, it will be n over n plus 1. Everything power n plus 3. All right. Now, what can I do here at this limit? It's a classic limit. If you remember, we may add and subtract 1 if we want, and it will be 1 minus 1 over n plus 1 power minus n plus 1. So that's classic limit from high school. And because I don't want to change anything, I have to multiply by the reverse. So in the end, everything becomes like this. Now, the limit from brackets, we know that's e. So this limit, all this limit becomes 6 times e power minus limit when n goes to infinity from n plus 3 over n plus 1. And now, how much it is n plus 3 over n plus 1? How much is this limit?
1.
Yeah, good. So it will be 6 times e power minus 1 or 6 over e. Well, you know, here I have to compare by 1. So 6 over e, how it is? Greater or less than 1?
Is greater.
Okay, so it's greater. So it means by the ratio test, what about the nature of this series then?
Is divergent.
Good, yeah, good. It's divergent, that's true. So the series is divergent by the ratio test. Yeah, is divergent. The ratio test.
I have a question.
Please.
Why did we simplify it n plus 1 here? 6 and in parentheses n plus 1.
Yeah. Okay. Let's look. So n plus 1 here probably. You have here a denominator n plus 1 power n plus 4. Well, with this one, if you look at the following limit, I wrote here n plus 1, but which power? 1 n plus 1 went away, and it remains only n plus 3. So here it's visible that we indeed simplified by n plus 1. Is it clear?
Yes, I understand. Thank you.
Okay, good. And a good question. All right. Other questions? Then let's continue with something else. So the E, it will follow exercise F. Okay, now let's take for instance n. Well, I will put here, yeah, n times sinus of pi over n. Power. I take this series. So here, I hope it's clear, it's sinus. The argument of sinus, it's pi over n. Okay,
Here we use the root test.
good. Very well. Yeah, you're right. The root test, somebody learned. Very well. So yeah, we use the root test indeed. So if I will denote by an the general term of the series, n times sinus of n, everything power n, remember that the root test tells us to compute the limit when n goes to infinity from so limit when n goes to infinity from root of order n from an. Yeah, by the way, the root test, the ratio test, the limit comparison test, the comparison test, I remind you the fact they are convergence tests used only for which are used. Okay, they are used, but they function. That's the main idea. This convergence test, they function only for series with positive terms, so be careful to that. Okay, but in our case, it's okay because pi over n, my series, but I will make a small correction here. It will start from 2. Okay, it doesn't matter because even if I leave n when n starts from 1, you know that sinus on the interval 0, pi, moreover, on 0 pi over 2, it has only positive values. So if I look a little bit at the general term, I see that's a series with positive terms, so it's okay to apply the root test. So it works for this situation. All right, let's start to compute the limit. Immediately I get when I apply root of order n from the general term, n will go away immediately. And we get limit when n goes to infinity from n times sinus of pi over n. All right, but what can we do now? What do you think? To compute this limit.
We divide by pi over n and then we multiply by n over pi.
Exactly. So what we do actually is to try to use that remarkable limit. I wrote it before, if you remember, the one from sinus of x over x. Yeah, that's the main idea. So sinus of pi over n, and I put it as 1 over n, but I need pi. I will put pi here, but I have to divide immediately by pi. So everything becomes pi, actually, because 1 over pi, it's pi. Pi, it's a constant. We put it in front of the limit, and we get only limit when n goes to infinity from sinus of pi over n, everything over pi over n. Okay, that's how much that limit.
1.
Right.
The limit I bounded, it's 1, but times pi, in the end, it's pi. Okay, pi, but pi, we all know that's a value greater than 1. So unfortunately, this series by the root test, it's divergent, unfortunately. Well, for us, that's not a problem. It's okay. Just we have to give an answer if it's convergent or divergent. Okay, so the series, yeah.
I do have a question. I mean, it's not really a question, more of a observation. We could also use B strong be necessary task because single limit is pi to the n will be infinity.
Sorry, I haven't understood what you said.
Putem să folosim criteriul, practic, primul criteriu necesar.
Okay. You want to use the necessary test, okay. And how we do it?
We calculate the limit of n.
The general term.
Yeah. And that will be infinity.
Yeah, that's true. So yeah, a good idea. Good point. Good remark. Yeah. So what we conclude from this is actually there are situations when we can use more convergence tests. So there are such situations where several convergence tests they are useful. So it's up to us to decide which one we prefer. Yeah, good remark. Thank you. Another one, and I think I will stop with this part. That will be the last type of exercise. Actually, that will be the last series we studied convergence. After that, I would like to do it and an exercise where we study the convergence, but also the absolutely convergence of a series, because at the exam surely you will have something like this, and I want to remember with you these things. Okay, let's take the series of general term n squared times e power 1 over n minus 1 minus 1 over n. And as I said, this is the last series we take. After that, we change a little the request. Okay, what can we do here? Some ideas, of course. Well, here.
We can use the comparison test.
Sorry.
Can we use the comparison test?
Well, I will wait for you to close the microphone. Yeah. Okay. Thank you. Yeah, we may use the comparison test. You may try, but an idea that will be useful here is just by curiosity to take the limit of the general term. Yeah, just let's take the limit of the general term and see what happens. So I will try to compute the limit when n goes to infinity from n squared times e power 1 over n minus 1 minus 1 over n. All right. Well, here, that n squared, an idea is to take it and put it at the denominator as 1 over n squared. I didn't change the limit, it's the same, but written in another way. Okay, and now, if I try to compute this limit, what I will obtain? If you just look a little and try to compute the limit, what we get? How much it will be at the numerator? How much is at the denominator?
It's 0 over 0.
It's 0 over 0.
So we will use the L'Hopital rule.
Exactly, we use the L'Hopital theorem. But remember that you can't use the L'Hopital theorem for sequences. Okay, but what can I do? I think I told you for those who have the seminar with me, I think I told you
So
several
you can
times.
take a function. So you can take a
Good.
function with this and then apply the L'Hopital rule.
Exactly, that's the idea. Good. Omer or who
I
was talking?
am here, Omer Genan.
Yeah. I recognized your voice.
Oh,
I was curious if I was true, but yeah, I recognized you. Good. Yeah, Omer, you're right. So I will construct a function immediately to be more easy for us to compute the limit after we construct the function. One idea is to let's take 1 over n and denote it by something by x. Yeah, and when I will do that, actually my function becomes e power x minus 1 minus x over x squared. Is it clear how I construct it? I took 1 over n as x. Is it clear?
yes.
Good. Now, I will compute the limit, but I will compute the limit when x goes to how much? I took 1x as 1 over n. So x goes to what do you think? Exactly. So I need actually limit when x goes to 0 from this function, or if I replace by f, I get e power x minus 1 minus x over x squared. Okay, now the L'Hopital theorem, it's easy. It's not too difficult. We derive. If you remember, we have to derive the denominator. We have to derive the numerator, and we get e power x minus 1 over 2x. Now, if we want, we may apply one more time the L'Hopital theorem, or just use the fact that e power x minus 1 over x is 1. Oh, well, I will apply one more time. L'Hopital, I get e power x over 2, which is 1 over 2. And this is it. So the limit of f, it's when x goes to 0, it's 1 over 2. But using the properties of limits, it means that the limit I need is also 1 over 2. But what I see here, so the limit of the general term, it's 1 over 2. It's actually different from 0. So what's the conclusion immediately? About the nature of the series, of course.
It's
Is it
divergent.
Exactly, it's divergent because of the necessary test. Yeah, remember that if a series, if the general limit of, if the limit of the general term is different from 0 or doesn't exist, it means that the series is divergent. Yeah, from the necessary test. So it's divergent. I write here, if it's not clear for someone, the necessary test. Okay, and I finished with this one. Okay, questions till now? No, because there is a revision, I would like also to revise with you that kind of exercise where I ask you to study the convergence and the absolutely convergence of a series, because you'll have something similar to the exam. So the following type of exercise, it will be to study the convergence and the absolutely convergence of some series. Okay. convergence of the following series. All right, let's take. I want to write all of them. I write one. We solve, we give an answer for this one, and then we go to another, and so on. So the first series I want to discuss with you today, it will be the series of general term minus 1 power n times the tangent of 1 over n. Okay. So let's start and study what happens with its convergence and its absolutely convergence. If you remember at the seminar, I advised you to start with the absolute convergence first, because if we are lucky and it's absolutely convergent, remember that it's also convergent, but that's not a rule. Well, I mean, it's not a rule to be absolutely convergent each time, because look at this exercise. When I try to study the absolutely convergent, by the way, let's remember a little from the course. What is an absolutely convergent series? Yeah, let's write the definition, because I'm not sure that everybody remembers. So, a series, remember that is absolutely convergent, and I prefer to write it this way. If, so a series of general term an is absolutely convergent if what happens? Who remembers?
The module of the general term is convergent. The series
Good.
of, yes.
Yeah, so the series having the general module is having the general term exactly the module of the first one is convergent. All right. Now, if we remember this, let's try to solve the exercise. I will take the module, the series having the module. Well, we get the tangent of 1 over n by applying the module, of course. Now let's see what can we do here. What ideas do you have? What about this series? How I study its convergence? What do you think we do? I will compare it with something.
Riemann.
With the Riemann series, yeah. So if we look at the general term, immediately I guess that I will compare the general term, the tangent, with 1 over n. Yeah, that's also a classic limit. Remember the fact that always the tangent of x over x, when x goes to 0, it has the limit 1. So by using this limit, it's 1. It's in 0 plus infinity. So I get that our series, it has the same nature as 1 over n, which is divergent, if you remember. Yeah, is divergent Well, it means that, okay, but with the divergent, let's look, the series having the module. But if the series having the general term, the module of the first one is divergent, so what's the conclusion about the absolutely convergence of the series? Is it absolutely convergent in this case?
No.
No. So it's not absolutely convergent. Good. So we gave an answer to this. Okay. Let's move. And so it's not absolutely convergent. Okay. But what happens with the convergence of the series? We have to give an answer and to this part. If we were lucky and the series was absolutely convergent, then the series is, we know that the series is also convergent and finished. But look that we have a case where the series is not absolutely convergent. Okay. What about the convergence now? To give an answer to this problem, I look at the series and I see that's an alternating series. Now, because we have an alternating series, what can we use here?
Leibniz.
Exactly, we use the Leibniz test. And because it's a revision, let's remind a little the Leibniz test first, and then try to use it in our situation. So the Leibniz test, for those who forgot, all right, what it says. Well, if we have an, a sequence of positive terms, decreasing, very important, decreasing, and with the limit 0. Then the alternating series is convergent. Okay, is convergent. Good. Now, let's come back to our series. I will lift a little the page to see it one more time. So, in my case, because I want to use the Leibniz test, will be an. Which term will be an?
Tangent of 1 over n.
Exactly, very well. Yeah, good. So an, in our case, we have the tangent of 1 over n. 1 over n, when n goes, it's from 1 to infinity, but when n it's 1, the tangent of 1, it's something positive, you know that it's pi over 4. When n it's greater or equal than 2, 1 over 2, 1 over 3, 1 over 4, and so on. All these, they are in the interval 0 pi over 2. On the interval 0 pi over 2, you know that the tangent has positive values. Good. But also, on the interval 0 pi over 2, I know that the tangent, I know something regarding its monotony. It's increasing or decreasing? What do you remember from high school? If you want, you may draw a little the graph of the function to see it better, yeah? In this way, we remember a little from high school. So if I take here minus pi over 2, here pi over 2, remember that pi over 2 and minus pi over 2, they are asymptotes of the function, and the graph of the function is something like this. But I need only the interval 0 pi over 2. If I look, at least let's look, if you don't remember from high school, let's look the graph from our drawing. What happens with the monotony?
This interval is increasing.
Good, yeah, it's increasing, but I have that 1 over n, it's greater or equal than 1 over n plus 1. Now, when I apply the tangent to this inequality, because the tangent is increasing, it won't change the inequality. So the tangent of 1 over n becomes greater than the tangent of 1 over n plus 1, which means that an, it will be how? Increasing or decreasing? Well, I have an greater or equal than n plus 1 if you look. So it is
Decreasing.
increasing, yeah. Yeah. Sorry. Yeah, my mistake. You wrote well. You said well. It's yeah, it's decreasing. Good. It's decreasing because I need to apply the Leibniz test. So I took an example where an is decreasing. So it's decreasing because an is greater or equal than an plus 1. We already proved that. All right, so it's decreasing. It has positive terms, and if I look at the limit of an, how much it is?
Zero.
It's 0. So now let's look. An has positive terms, is decreasing, and has the limit 0. So I see that actually the Leibniz, the conditions, all the conditions for the Leibniz test are verified. So it follows immediately that the series from our exercise, it will be convergent, yeah, from the Leibniz test. All right, and we finished. So is convergent, yeah, by the Leibniz test. What we see is that here we have a series which is not absolutely convergent, but still is convergent. Okay, and we finished. Questions? As an exercise for home, so the following exercise, it will be similar, let's say, but I will leave you to work by yourselves at home. I will take an alternating series, the series of general term minus 1 power n, everything over n times 5 power n. What I want you to do is to study its absolutely convergence and its convergence too. I leave you to do it by yourselves. It's easier than what we work. So as a small exercise, just to apply what we talked about and see what you get. Okay? Good. And now, the second part of this meeting, I'd like to revise the chapter of power series. This chapter is also included at the exam, and let's work some exercises. So a small title, the second topic of discussion, power series. Okay. And the first type of exercise we'll work, it's to determine the domain of convergence of a power series. If you remember, we worked this kind of exercises at school, yeah, at the seminars. Let's do one more exercise. So, determine the domain of convergence. For the power series, actually I will take the following series, and it starts from 1, and the series, it's 2 power n times x plus 2 power n, everything over square root of n times n squared plus 1. Okay. Let's see. What can we do for this series? It's a series of functions, if you look. And what I learned you to do for this situation?
We denote x plus 2 by y.
Exactly. So we start by using a change of variables. Okay, if I do that, so I will denote by x plus by y x plus 2. So immediately I get a new series. It will be 2 power n times times y power n, everything over square root of n times n squared plus 1. Why I do this? Why I do this change of variables? Because I want to obtain a power series and then to apply the theory I know from power series. Now, for the series in Y, I have indeed a power series, so I can do what I learned for power series. I will determine the radius of convergence. And remember that we had two formula to use for the radius of convergence. Which one do you advise me to use here? What do you think?
The module?
Yeah, but the module of who?
Of square root from n of this.
Well, I think it will be more useful to use the one with
No, it's better
AN.
with the ratio.
Yeah, exactly.
It's better.
I will put the module, but if you see AN, it's positive, so actually we don't need, but I write it, and then when I replace, I won't put the module anymore because I see that these terms are positive. So I have 2 power n over square root of n times n squared plus 1 times the reverse of an plus 1. It means that we will have square root of n plus 1 times n plus 1 power 2 plus 1, everything over 2 power n plus 1. Okay. I will simplify by 2 power n. We remain with 2 here. So it will be 1/2 in front times limit when n goes to infinity from what we have. It will be square root of n plus 1 over square root. I will group the terms to be more easier for us to see how much is the limit. Also, we have n plus 1 power 2 plus 1. We get n squared times 2n plus 1 plus 1, it will be plus 2. Everything over n squared plus 1. But now, when we compute the limit, square root of n plus 1 over square root of n, how much is the limit of all this when n goes to infinity? It's 1. All right. Also here, because we have the same degree, we can say directly how much it is. 1. Yeah. So this limit is 1, but with 1/2 in front, we get 1/2. Okay. Now, what I see that the radius, it has a value different from 0 and finite. So if we remember the Abel's theorem, it implies immediately that the series in Y, it will be convergent. So the series in Y, 2 power n times y power n, everything over square root of n times n squared plus 1. So this series, it will be, sorry, I don't know what happened. So is here. I know that it's odd. Okay, so it's convergent for y in the interval. Okay, so is convergent for y in the interval minus 1/2, 1/2, and divergent. Do you have questions? If not, don't forget to close your microphone. So questions till now? Okay. And divergent, I said, for y in the interval minus infinity minus 1/2, reunion by 1/2 plus infinity. Okay, now to finish this exercise, what I have to do?
To see what happened at the extrema.
Exactly. I'll take 1/2, then minus 1/2, and check the nature of the series in these situations. All right, let's say I take y be 1/2. By replacing by the value of y, we get, let's see how much we get. It will be 2 power n. Instead of y, I will put 1/2 power n. Everything over square root of n times n squared plus 1. But I see that 2 power n goes away, and I get only 1/2 square root of n times n squared plus 1. Okay, what about the series? Can you tell me immediately another one having the same nature with my series?
1/n squared plus 1.
1/, louder.
N squared plus 1.
Well, it will be 1/n power 2 plus, don't forget that you have square root of n, it means n power 1/2. So I will take n power 2 plus 1/2. Is it clear?
Yes.
Mm-hmm. But this series is actually the series, the Riemann series. Yeah, if you look, it's the Riemann series of general term 1 over n power 5 over 2. It's a Riemann series with alpha 5 over 2. So what happens? How it is? What do you think?
Convergent.
Good. Is covered. Yeah. Okay. So in why it's 1 over 2, the series is convergent. Okay. To finish, I have to check and for the other extremities, and then that will be all. So if I take y be minus 1 over 2, by placing by its value, I have 2 power n times minus 1 over 2 power n over square root of n times n squared plus 1. Well, I continue, I get 2 power n times minus 1 power n. 2 power n comes to the denominator, n squared plus 1 times square root of n. So I have this. 2 power n, you see that can be simplified, can be reduced, and I remain with the series of general term. Minus 1 power n over square root of n times n squared plus. Okay, and now let's see what about this series. How can I study its convergence? It's an alternating series, if you look. Yeah. What we do?
We will use the Leibniz test.
Exactly. We use the Leibniz test. In our case, I take an be 1 over square root of n times n squared plus 1. It's obviously that verifies all the conditions from the Leibniz test. So the series is convergent in this case too. Yeah, and I will write between the parentheses what convergence test I use. Okay, so in the end, I remark the fact that now by concluding, in 1 over 2 it was convergent, in minus 1 over 2 it's convergent too. On the open interval minus 1 over 2, 1 over 2 is convergent, good. So in the conclusion, why? It means that it's in the interval closed both sides, minus 1 over 2, 1 over 2. But I don't need y. Now is the moment to remember that actually we need the value of x, but y it was x plus 2. So x plus 2, it's in the interval minus 1 over 2, 1 over 2. Which is equivalent to the fact that x, well, if I will make the computations, how much, what interval I get. It will be minus 1 over 2 minus 2, which is minus 5 over 2, and 1 over 2 minus 2, that's minus 3 over 2. Yeah, and I finish. Yeah, so the domain of convergence for this exercise, the domain of convergence, it's minus 5 over 2, minus 3 over 2, and we finish. Okay. Questions? Then let's solve another type of exercise that also it's a high probability to appear at the exam. No. For the next exercise, I will ask you to compute to determine the domain of convergence, but also to compute the sum of some series, of some power series, of course. So let's write the request, determine the domain of convergence. And compute the sum of the series. Right. And the series, they are, immediately I will write them. The first one I will take, it's the series of general term -1 power n times x power n over n. And the second one, B, we have the series of general term -1 power n times x power n plus 1 over n. Okay, so the first part of the exercise is something similar to the previous exercise. It asks us to compute the domain of convergence. So we'll do exactly what we did at the previous exercise, with the exception that we don't need here to use a change of variables. Yeah, because we have power series. Yeah. But if we look a little at the first exercise, here there is a possibility to make a change of variables if we want. Which one? It's not mandatory. Yeah, you may do it and without a change of
We can
variables.
denote x at power 2 with
Exactly.
y.
Yeah. So it's not mandatory here. We may do it without this change of variables, or if we want, we may do it. But this change of variables, actually, it will help us a little bit when I will try to compute the sum. So yeah, it's good to, it's better actually to use it. Okay, but to be clear, the fact that for the domain of convergence, it's not mandatory to use this change of variables. We may do it and without using it. Okay, but I already took yx squared, so now we have to continue like this. As we did before, I will get a series in y. All right, for this series, I have to determine its radius of convergence. And in my case, it will be -1 over n. So I see that here there are also negative terms. All right. For the computation of the radius, I will use also the formula with the module of an over an plus 1. Let's start and perform the computations. They are easy, just we replace here. I have -1 power n over n times the reverse of an plus 1. So it would be n plus 1 over -1 power n plus 1. Okay, because we have the module, everything with -1, goes away, it will be 1. So we get only limit when n goes to infinity from n plus 1 over n, which is 1. Okay, so the series in Y, it will be convergent from what we learned till now. The series in Y, I repeat, it will be convergent for the interval -1, 1. So for Y in -1, 1 and divergent and divergent for Y in -infinity -1 union by 1 plus infinity. Okay, now as we did in the previous exercise, we have to take and study for the extremities. So I take for Y equals to 1, we get immediately some and now when I take Y B1, we get the series of general term -1 power n over n. It's an alternating series. By the Leibniz test, what we have immediately?
We find out it's convergent.
Yeah, it's convergent by the Leibniz test. Okay. It's convergent. The Leibniz test, I write here. Also, please, at the exam, I want you to write the results you use. All right, let's see for the other extremity what we get. When Y is -1, well, I will get the series of general term -1 power n over n times -1 power n. Well, this one, if we look, it will be exactly 1 over n, because we get at the numerator, we get -1 power to n, which is always 1. So the series we get in this situation, it's is the series of general term 1 over n. What we have here?
We know it's always convergent.
It's always? Sorry, it wasn't very clear what you said.
Convergent.
It's convergent, it's divergent.
Oh.
Isn't it? It's the harmonic series.
Yes.
Yeah? Remember. Okay. So let's remember, because I said today it's a revision. Let's take the Riemann series. Yeah. It's a series of general term 1 over n power alpha. What we know about it is convergent for alpha strictly positive and divergent for alpha less or equal than 1. Is it clear now?
Yes.
All right. Then, to conclude, what happens with Y? In which interval it will be? Well, in -1, we see that is divergent, so it's open here, but at 1, it will be closed. Yeah. Okay, but don't forget the fact that actually Y is x squared. So x squared in which interval must be? I can't take -1, 0, isn't it? Because x squared is always positive. So it will be only in 0.
0, 1.
Exactly. But from here, it means immediately that x is in the interval -1, 1. and we may take it close both sides. Yeah. To be sure that in -1 is convergent, let's take our series where it is here, yeah, and replace x by -1. How much we get the series in this situation? It will be the series of general term -1 power n times -1 power to n. How much it is always? 1, isn't it? So actually what we get is -1 power n over n, which I know that's convergent from the Leibniz test. We had it before. So x remains in -1, 1 closed. Okay, and the first part of exercise, it was solved. Now, let's take and do the second request of the exercise to compute the sum. What I do? Well, I learned you at the seminar to denote by something its sum. But here at this exercise, I think it will be more easy to take the change of variables we already did, y be x squared. So I will take and denote by sy the sum when n is from 1 to infinity of the series in y of -1 power n times y power n over n. Okay? Okay. What can I do for this series? I learn you to do what to do, to integrate or to derive term by term. What do you think is suitable here more?
We can derive.
Exactly, good. I will derive, so s prime of y becomes sum from 1 to infinity from -1 power n times n times y power n minus 1 over n. I will simplify by n, and everything becomes sum from 1 to infinity. But that -1 power n disturbs me a little. I prefer to put -1 in front and write it as -1 power n minus 1. And if you look the power of y, you will get why I did like this. I didn't change anything, but instead of -1 power n, I wrote it as -1 times -1 power n minus 1. And now, if I will make another notation, let's say, I will take n minus 1 be k. Actually, if I take like this, I get minus the sum of the series from, and now let's take k. If n it starts from 1k, it will start from how much?
0.
Exactly. So I get sum from k equals to 0 to plus infinity from -1 power k times y power k. But this actually can also be written as sum from k equals to 0 to infinity from -y power k. Do you agree with this?
Yeah.
More. Remember that we have the following formula. We discussed it at the seminar, you studied at the course too. In general, 1 over 1 minus x, that's the sum of the series of general term when n starts from 0 to infinity from x power n for any x such that its mod will be less than 1. Okay, but in my case, okay, it doesn't matter if I have x or y, which variable I have. But now, because I have here minus y, can you tell me how much will be this sum? By using the previous
1
formula.
over 1 plus y.
Exactly, it will be 1 over 1 plus y. Good. And let's see what we get. I got actually the fact that S prime equals to minus 1 over 1 plus y. Well, so let's write one more time to have in front of our eyes the result. So S prime is minus 1 over 1 plus y. Now, how can we determine S from here? We can
integrate.
exactly, so it will be integral, well, minus the constant goes in front, minus integral from 0 to y, I don't know, I will take another variable here, let's say t dt. Its primitive, I hope everybody knows, is the logarithm of 1 plus t. So we get immediately minus the logarithm of 1 plus t computed from 0 to y, or written, or if I replace, I get minus the logarithm of y plus 1. And one more step to do. I don't need the series in y. I need actually the sum of the series in x. So if you look the series, we need the one in x. It's exactly s of, so the one in x power to n over n. That's exactly s of x squared, but by replacing instead of y, if I will put x squared, I get everything be minus the logarithm of 1 plus x squared, and that's it. Yeah, we finished. So the sum of the series is exactly minus the logarithm of 1 plus x squared. And now is an application. For instance, if I take, let's look, so application. Yeah, these things are very nice because they help us to compute the sum of some series or some series of numbers. For instance, if I take, I don't know, x, b, 1 over square root of 3, let's say. Well, by replacing in our series, we get, so the sum of the series of general term minus 1 power n times 1 over square root of 3 power to n, that's actually 1 over 3 power n times n. So look what we get. We get that the sum of this series, it will be the logarithm of 1 plus 1 over 3, which is exactly, if I write one more time, that will be exactly minus the logarithm of 4 over 3. So I will write one more time what I got. That minus, I can multiply this equality by minus 1, and actually becomes everything minus 1 power n plus 1 over 3 power n times n equals to logarithm of 4 over 3. Yeah, so I got the fact that the sum of this series of numbers, it has the value logarithm 4 over 3. And this is it. Yeah, so this chapter, power series, it has nice applications when it comes to the computation of series of numbers. All right. Questions?
So at the test, you need to make this application at the last thing.
I don't know. Let me think. I haven't decided yet. I have to talk with the professor regarding the subjects, but
No,
I don't think.
I mean this thing for x equal 1 over square root of 3.
Well, it may give you something, I don't know, to compute the sum of a series of numbers. But of course, first you will have probably the power series, so you will know what to do. But I managed to answer to your question.
No, because you made like a verification in the.
Yeah, just, you know, for instance, so let's say you have this exercise I solved with you at the
Okay.
exam. So let's say that's the first part. Let's say A, the point A. At the point B, I can ask you, for instance, I don't know, compute the sum of the series of general term minus 1 power n plus 1 over 3 power n times n. But,
Okay.
you know, after you solve the point A, the one you are asked to compute the sum of the series, it will be easy for you to remark that if you take x b1 over square root of 3, you get exactly the series I asked you to compute. It's a sum. But
Okay.
no, I don't think it will be like this. Just I wanted to solve it to something. I think it's interesting, yeah. But no, I don't think you'll have something like this at the exam. Yeah,
Okay.
it's
Thanks.
better like this.
Yes. Now it's good.
Yeah.
Thanks.
Good. Okay. All right. Because it's late and I solved already an example with you, I will leave exercise B as homework. At the next meeting, by the way, I know that I announced you that the calculus lessons with me, they will be on Monday and on Wednesday too. But there was a change. I'll have these lessons only on Monday because on Wednesday I will have linear algebra lessons. You are invited if you want. The only problem is that these linear algebra lessons, they will be in French. If you want to come, well, you are more than welcome. But somebody has to, just a little to stop the recording.